Hi, my name is Hassan Deep. I'm a PhD candidate and general research fellow at the University of Tartu. Today I will be presenting my work, BigFeat. It's a scalable and interpretable automated feature engineering framework. This paper is a joint work with Shota Amashukeli, and Radwa Ishawi. I would like to start my presentation with a quote for Peter Norvig, the great scientist. He says, more data beats clever algorithms, but better data beats more data. And this presentation will be all about improving the quality of the input data for machine learning models. As you all know from the machine learning perspective, when we have a nonlinear relationship between the independent variables and the target variable, usually machine learning engineers tends to prefer complex models like neural network support vector machine and ensemble models. Although these models can learn a task-specific patterns, but they still need a massive training instances and they are hard to trust, especially in sensitive domains like in the medical sectors and financial domain. That's why most machine learning experts tend to use some feature engineering tricks so that they can transform this nonlinear relationship between the features and the target variable into a linear relationship. So they can use any machine learning model or even simpler machine learning models can perform well with these linear relationship between the input and output. Let me give you a motivating example. Here we have a promotional data set where we have some information about the person. These promotions are sent to him, are sent to some promotion information about the promotion itself, the number of promotions sent so far to this customer, and the number of promotion used by him, and whether he used the current promotion sent or not. Let's use some feature engineering trick to generate some useful feature and try to make the relationship between these features and the target variable more easier and simpler. So let's first sort the data based on the number of promotions sent for each customer. So this is customer number 20. And for each two consecutive rows, we subtract or calculate the difference between them. So 1 minus 0 is 1, 1 minus 1 is 0, 2 minus 1 is 1, and so on and so forth. We notice that this is the difference, which represents whether the customer has used the previously sent promotion or not. This column, the difference is almost the same as the target column, and the relationship between them are now simpler and easy to capture by even simpler models. The question now is, can we automate this process, the process of engineering these features in automated way? And the answer is yes, of course. We can do this under the assumption that we assume that we have some transformations. This transformation could be uniform, binary transformation or unary transformation. For example, if it is unary transformation, we can have the arithmetic log, square root, e to the power x, where x here is the original feature, one of the original features, and binary transformations like the arithmetic sum, multiplication, division, and so on. Maybe we have also trinary transformations or operators. And if we can select the most important features and apply the most useful transformation on them, then we can really generate some insightful features that help the model improve its predictive performance. Mostly, these automated feature engineering tools fall into two main categories. The first one is generate and select. The second is iterative reduction. For the first one, generate and select, these automated feature engineering tools tends to start by generating an extensive pool of feature. This is very large pool of feature. They extract features by applying the transformation over the features again and again and again. So for example, here, this is the original features, applying the transformation e to the power x to all of them, the square root, and they even can, and then they can concatenate some features so they can apply, for example, e to the power of this generated feature, and the number of features is increasing, as you see, exponentially. Then eventually they apply a final feature selection step where they reduce the number of generated features and report them to the machine learning model. For the iterative reduction paradigm, they iterate between extracting some features and reducing the number of generated features into a smaller feature pool, and again feature extraction, selection, and so on till they eventually report the eventually selected feature. As you may notice, the first set or the first group of automated feature engineering tools, which falls into the category of generate and select category, they suffer from two main problems. The first one is they are really memory intensive because the number of features is increasing exponentially. They suffer from the curse of dimensionality, and usually they have a lot of memory errors. Also, the process is sequential, so they cannot it can't be parallelized, so it's not scalable. For the second category, iterative reduction, uh, they may miss some important feature. How may this happen? Uh, so at the preliminary feature selection, they may drop some features which are not important at the current stage, but in the future or in the following steps, if we combine them all together, we may generate more useful features. The same thing that happens with the deep learning way of feature extraction, where you when you add up or concatenate some primitive features in a deeper way, eventually they lead to very insightful and important features. Also, it's really time intensive. In our paper, we solve, or on our tool, BigFeat, we solve these two main and the problems of the two main the two main categories of automated feature engineering tools using our tool, BigFeat, in two subsystems. We refer to them by dynamic feature generation and stability feature selection. We will explain them in details in the following. Now to our proposal, BigFeat. Um, The design goals and objectives while we were designing and implementing BigFeat were to design and implement a really user-friendly tool, so the user can easily use it, and the feature generated from this tool has to be or have to be interpretable features. We mean by interpretable features that the user can always relate the generated features into the original one. The tool also has to be scalable. So most of the BigFeat components could be easily parallelized. And the predictive performance of the machine learning model has to be also model agnostic. It's not tied to a specific category of models or some specific models, but all the models should witness predictive performance improvement. Okay, now let's move to the problem definition before solving the problem. As you all know that for any machine learning problem, we have an input data set. This input data set has some independent variables. We refer to them by features or X for short, and some dependent variable, the target variable, we refer to it by label or Y for short, and we split or partition this dataset into two splits, the training split and test split. We use the training split to learn some transformation function that can easily transfer these features into a new space, or generate some engineered features that's expected to improve the predictive performance when we used our machine learning model. So basically, we are searching for a function psi. When you use it to transform the test split and calculate the predicted target variable, compare it to the original or the ground truth, and we calculate the loss. This is the function that will minimize the loss, psi that will minimize the loss. Okay. Now to the framework itself. The framework is a probabilistic framework that follows two main steps: feature generation in blue here, and feature selection in this is the yellowish color. For the feature generation, basically we are trying to select the most important features and apply over them the most useful transformation so that we generate really insightful features that help improve the predictive performance of the machine learning model. We repeat this iteration again till we generate a feature pool. Then we reduce and select the most important feature using a technique called stability feature selection. And if we remove the if you have some correlated features that linearly correlated, we remove the one of them, and we update the operator importance for the following iteration so that the in the next iteration the feature generation is done in a smarter way. So we select in a smarter way the most important operators. For now, we talk about every step of this in more details, and we start by initializing feature and operator importances. For the feature importances, we train some tree-based models over the original feature, and we take or consider the information gained from these tree-based models as the feature importance. So we have multiple models, so we aggregate all the information gained from these models and aggregate them, normalize, and consider these to be the feature importance of the original features. Initially, we don't have any virtue for any transformation or operators over the others, so we initialize the operator importance using a uniform distribution. So second, we mine the feature combinations. The feature combinations, we expect them to work better together. So we do this under two hypotheses. The first one is that we assume the split features are more important than non-split features from the decision tree based models. Secondly, features that appear together in the same path, this is the paths which are used to predict the value for instance or for the input instances. These features that appear together in the same path are expected to work well together. So we use these two hypotheses to generate a combination matrix. Each element of this combination matrix represents the number of times these two features I and j have appeared together in the same path. Okay. Uh, then we move to, so before moving, we use this combination matrix again to give more chances to these features that appear together in the same path, to give them more chances to get selected together and lower chances to feature that didn't appear together in the same path, and of course lower chances for non-split features. And then we move to the dynamic feature generation. Now, so now we know how to select the features and the importance. Now to the point where we dynamically generate these features. So we've in this step we follow the lazy evaluation mechanism where we generate the computational graph first, and this function receives the height of the expected height of the computational tree, and as long as this height is not zero, we continue to sample operators. So at the beginning, because h is 2 not 0, we sample one operators, which here happen to be the division, and because division is a binary operator, we subtract 1 from the height, so it is now 1, still not 0. We sample again two operators. The linear, here it happens to be the linear operation and the multiplication. Subtract 1 from the height, and because it is 0, we start to sample features for this. And this is the price per square meter, for example, and we can generate the Euclidean distance using the same technique. Euclidean distance may be very important for many applications. For example, if we are solving a house pricing problem, the distance of the house to the center is a critical feature that is expected to improve the predictive performance of the model. Okay, so we continue doing this till we generate a pool of feature consists of kn features, where n is the number of original features, k is an arbitrary number. Then now we want to reduce the number of generated features using a technique called stability feature selection. So we train a number of machine learning models. Each of them is trained over a sample of the features, and sorry, on a sample of the instances, and we aggregate the feature importance from all these models. So we're not tied to any of them, and the feature importance are model agnostic now. And we normalize and consider this feature importance to be the metric that we will use in order to select the best or the most important N features. Within those most important in features, if it happens, we found that some features that is really correlated, that has linear correlation between them, we use Pearson correlation for this. We remove the least important one and we add the one more feature from based on the rank from the previous step. Okay, so to improve the quality of the feature generation in the following step, we mine and update the operator importance, because initially we, as if you remember, we initialize the operator importance using a uniform distribution, so all of them are the same. But after the first iteration, this distribution will change. For example, if we want to update the importance of the submission operator, we count how many times this operator participated in the selected features. So assuming x1 to xk are the important and selected features, we count how many times we witnessed or we saw this we see these summation operators. So here it happens to be 6, for example. So we add 6 here to the importance vector, and we do the same for the remaining operators. Then we normalize and we consider the output to be the new operator importance for the following iterations. So this is it. Two main steps: feature generation followed by feature selection. We analyzed all these steps, the complexity of them, and uh, our tool after the analysis we found that our tool has a linear complexity of memory and computational complexity. So we have computational and memory. We have a linear complexity of computation and memory space. To evaluate our tool, we conducted two main experiments. The first during the first one, we fed the original features without applying any feature engineering over these features into a machine learning model. We record the F1 score. We engineered in the second configuration. We engineered these features using the state of the art framework called AutoFeat. We record again the F1 score and we engineer this feature, construct new features using our tool BigFeat, and again we record our F1 score. The machine learning models used here were 8 different machine learning models, and this is the first experiment conducted. For the second experiment, we wanted to test if the predictive improvement that happened in due to the feature engineering phase here is still consistent if we tuned and improve the quality of the used machine learning pipeline. So we want to still to study if we can still improve the performance of a machine learning pipeline that is selected and optimized for the input data set, and the hyperparameter of this pipeline has been tuned in a systematic way. So we used the AutoML framework for this task: Auto, Scikit-learn, and Tpot, and the same 3 configurations: original features, engineered feature using AutoFeat, and engineered features using our tool BigFeat. And we tend to also to record the F1 score for all of them. For the second experiment here, these are 3 different data sets. As an example, these are the 3 different configurations, the 8 classifiers, and we see that the performance of BigFeat outperforms the two different configurations, the original and AutoFeat. For the second experiment, where we use AutoML, again, BigFeat statistically outperformed the performance of generated using AutoFeat or original with a statistically different significant with statistically difference uh, over AutoScikit-learn in the first graph and over tpot in the second graph. We studied also how well our tool is performing and the added and the added predictive performance improvement over different iterations. And as we see here from these three different examples, that the predictive improvement is increasing over time, then it plateaus almost after the 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 fifth or the seventh iteration. That's why we didn't use really deep or iterations more than 7 times. We also studied the contribution of the generated features to the original one. So we monitored the selected features to see the percentage of generated features compared to the original one. And as we see over these different 10 data sets, the majority of the selected and important features were generated using our tool. The execution time is also studied, comparing BigFeat to AutoFeat, and the execution time of BigFeat was extremely better than AutoFeat. BigFeat was 22x times faster than AutoFeat. Here in order to be able to see the column of BigFeat, the execution time of BigFeat, we applied the arithmetic logarithmic over the y-axis, so we can see both of them all together. And as you see, BigFeat is extremely faster than AutoFeat. To conclude, we can say that we developed and implemented an automated feature engineering tool called BigFeat. And the tool has improved the performance of 8 different machine learning models with average performance of 4.59. And the execution time of BigFeat is extremely fast. It's 22x faster than AutoFeat. The performance the performance complexity and the running time and memory space complexity is linear for our tool, and this confirms the scalability of BigFeat. That's all from my side. Thank you very much, and I will be happy to take your questions. Thanks a lot.